Hi to all. Today we're having our first ever speaker back again, exactly 1 year after the first ever paper reading we did. I think it was actually May 11th, 2022. Vlad Lialin is a PhD student from the University of Massachusetts Lowell. He has previously interned at Google, Apple, and Amazon Alexa AI. Today he's going to talk about 40 different works published in the last 4 years, which in large language model years is pretty much 4 centuries. Even since he gave his last talk with us, so much has changed. So thank you, Vlad, for coming back, and we would love to listen to what you have to say today. Thanks for coming back.
Yeah, thanks. It's nice to be back. All right. So I had to modify my 15-minute presentation for this talk. Hopefully, we will be able to cover many more methods than I did before. So I guess let's begin.
Can I just interrupt for 1 second? If people have questions, would you prefer me interrupting you and reading them off the chat, or would you like to do a Q&A session separate at the end?
Please do interrupt.
Okay.
The best way for me.
Okay, so guys, just put your questions in chat, and I'm going to interrupt Vlad and to read them out to him. Thanks.
All right. Thanks for a nice introduction. So I want to talk about parameter efficient fine-tuning and our new survey on this topic. It is a joint work with me, Additive PEFT, and Anna Rumchewski. All right. So first is, like, as long as I remember deep learning, for me, like I started getting into this field in like 2017 or something. Like stack more layers has been super promising approach, and it seems to just continue going. And now the best models that we have, they can even explain this meme and do this pretty well. And model sizes continue to grow. At least we thought so until maybe like a month ago. Now it's slightly differently. But the fact is that we saw extreme growth from like the biggest model size being like 350 million parameters, BERT large in 2018, to the biggest model available right now is Bloom with 176 billion parameters. And GPU RAM does not grow as fast. And this is like the biggest problem in deep learning, like how to get more RAM. When I saw the news that NVIDIA announces H100 with 160 gigs of RAM, I was like, oh, wow, this is like, I would dream to get like my hands on this GPU. And yeah, let's take a look at BERT. If you go to their GitHub, like nobody goes to BERT GitHub anymore, I guess. But when they released this, they had to add a section of out-of-memory errors. And they were saying, okay, guys, like these are pretty large models. And if you have like a consumer-grade GPU, these are the batch sizes you can work with and sequence length you can work with for BERT base and BERT large. Notice that for BERT large, at sequence length 384, 512, your maximum batch size is 0, which is not very useful. And we can work with 0 batch sizes. It's very tricky. You can do like model parallel or like some other fancy stuff. But the main fact was models are becoming bigger than the GPUs. And okay, at the time of BERT, we were worried that these models are super expensive to pre-train. Like regular researchers, regular like people who are just into deep learning, they cannot really do this scale of the research. We cannot pre-train models that are like 300 million parameters or maybe even 100 million parameters. It's kind of expensive to pre-train. But now we're in a different world. Like for some time, we've been in a world where we have these amazing models released, T0, 10 or 11 billion parameters, and like more billion scale models. And at some point, we couldn't even pre-train them, not pre-train them, but fine-tune them. And at this point, you're like, okay, I can inference this model on my GPU if I do like int8 and something else, but that's kind of it. Like I need to get like a small cluster to actually tune it to my task. But now with the progress of parameter efficient fine-tuning and some other optimization techniques, we see something like this. This is Deep Speed Chat. It is a pretty nice library to do reinforcement learning from human feedback, and they really tried to optimize everything they could. And here you come from, okay, we cannot fine tune 10 billion parameter models, or like 300 million parameter models are huge. You go through, you can train a small or toy model, for example, 1.3 billion on consumer grade GPUs in about an hour. So how do we get from canned to toy model just an hour? First, let's just talk about memory. Memory is the biggest problem in deep learning. And if we're training transformers, this is roughly what you spend your memory on. You spend your memory just for CUDA. CUDA just takes this gigabyte of memory, like you cannot do anything with it. It's just some precompiled kernels and stuff like this. You spend the memory on your model weights. Again, can't really avoid this. Your memory needs to be in the memory, or you need to do some hacks. You need memory for your gradients to update your model. You need your memory for the hidden states, and you need to store these hidden states if you want to backpropagate. And you need memory for the optimizer states. And actually, like, people kind of tend to overlook this, but Atom takes twice as much memory as model weights, because for every parameter in your network, Atom has to keep track of two parameters, first and second moments of the gradient, to do efficient optimization. And if you work with something like FP16, you also need to store FP32 copy of the gradients. So if we take all of this and just estimate how much memory is spent on fine-tuning OPT 1.3 billion in 16-bit float with sequence length 512, this is what we get. 1 gig just for CUDA, 2.5 gigs for the model weights, same for the gradients, about 1 gig for hidden states, 5 gigabytes for optimizer states. And if you work in 16-bit float, you kind of want 32-bit for the copy of the gradients for your gradient accumulation, which takes up 10 gigabytes. So kind of best case, you spend like about 12 gigs of memory just to hold one batch of data. In the worst case, you spend like 20-something gigs, which is starting being expensive. And this is just batch size 1. And this is my secret formula for hidden state estimate. It was kind of tricky to compute it, and it's slightly incorrect if you saw like estimate versus actual. So if anybody has any directions for better formula or can see any issues with this one, I will share the presentation. You're very welcome to contribute. So let's say we can train less parameters. Let's say we can train maybe 200,000 parameters for the model. How much memory would we spend? In this case, we have 2 parameter counts. One of them is just model parameters, and one is trainable parameters. So if our trainable parameters is just 200,000, then our gradients go to basically 0. Our optimizer states go to like 0 times 2. And our copy of the gradients, if we're doing gradient accumulation at P16, goes to like 4 times 0. So you can really neglect how much memory you spend on this, and you get go from about 11 gigabytes to just 6 gigabytes of required RAM. So this basically allows you to have twice bigger batch size or twice bigger model. So does this work in practice? Can we really just fine-tune a few parameters and get decent performance? Actually, yes, there are many methods, and we'll discuss a couple of them that do this. Some of them are clever, some of them are stupid, some of them are amazing. All of them work at some level, and I think some of them are overlooked. But the fact is, LORA, probably everybody heard about LORA, is this amazing method that can fine-tune your networks up to the size of GPT-3, 175 billion parameters, with just a few added parameters, and get more or less the same performance as fine-tuning of the full network. So let's get into parameter efficient fine-tuning. Any questions so far? So we took a look at the field of parameter efficient fine tuning, and probably one of the first papers that started doing this was adapters paper, BERT adapters. And it was like, again, 2019 or something. Since then, many new things appeared, like LORA, like BitFit, like KronA, like prefix tuning. And we tried to summarize all of them and see, okay, what are the similarities between the methods? And we came up with this taxonomy. So mainly there are three big classes. There are additive, there are selective, and there are reparametrization-based parameter efficient fine-tuning methods. And additive is so large that we had to have like two more categories in additive. One of them is related to adapters, and one of them is to soft prompts. So let's go over some of the examples of these methods and think about their pros and cons. So adapters, probably the first parameter efficient fine-tuning method, which was promoted for slightly different things when the paper came out. They were more talking about the storage of this because fine-tuning BERT wasn't that big of a problem. The idea is pretty simple. You go into your transformer, which mostly consists of just multi-head attention and a fully connected network. And you insert fully connected networks in between these layers. And you make sure these extra FCNs are kind of small. So you select a pretty small internal dimension, and this is a rough pseudocode. So you have your self-attention, you have your inserted adapter, then you have your layer normalization, residual, FFN of the transformer, and another inserted adapter. And you only update the parameters of the adapter. You do not modify the weights of the transformer. And this works pretty well. And this method was evaluated on many different networks, many different sizes. And we'll talk about the performance of all of these methods towards the end of the presentation. I think I saw a question in the chat. Can we compare distillation to small model and parameter fine-tuning? So I think both of these things, distillation and PEFT, they kind of target the same problem of like, we want to save resources, but parameter efficient fine-tuning is more of like, how are we going to modify a super large network with limited compute? While distillation is, we have kind of unlimited compute at train time, but we want very limited compute at inference time. We want to compress our network. So honestly, you probably cannot do distillation of super large networks and limited hardware because you need to inference your large network and train your small network. With parameter efficient fine-tuning, you hopefully can fine-tune very large networks. Hope that makes sense. So next example is prompt tuning. So this is second big group of additive PEFT methods. And the idea is, it came up kind of like from two sides. So there were two papers that introduced more or less the same idea, more or less at the same time. And at that time, prompting has started being a thing. We were saying that like, oh, actually, if you fine-tune a prompt BERT correctly, you can get similar performance to GPT-3 in terms of few-shot learning. And then it's just became kind of wild. And at some point, people were like, okay, how do we find these prompts? How do we find these verbalizers for our classes? For example, maybe the things like spam and ham are not the best for like spam classification. Maybe you can find better words, or maybe you can explain tasks better. So at some point, people were like, okay, let's just fine-tune our prompt. So let's take this part of the prompt, just prepend it to the input and fine-tune it. And more or less at the same time, alternative method did more or less the same, but instead of prepending something to the input of the network, it prepended something to the keys and the values of the network. So if this is our transformer, what prompt tuning does, kind of a standard way of doing this now, it concatenates the keys with some extra trainable parameters and concatenates the values with some extra trainable parameters and only trains this prefix. And you do this for every single layer. So yeah, prompt tuning attention would look roughly like this. You compute your queries as usual. When you compute your keys, you concatenate your yes, your trainable parameter for the keys and your input. You compute your keys. You do the same for the values, and then as usual attention. This was also a pretty cool method, and it's super parameter efficient in terms of how many parameters do you add to the network, because like all you add is just like some hidden state times the number of extra tokens, and the number of extra tokens is usually very, very small, like 5 or like 100. In case of 100, it's becomes a bit more interesting because you start thinking about inference cost, but we'll cover this toward the end of the presentation. So next class is like additive PEFT that does not look like prompt tuning and does not look like adapters. And there are a few of like pretty interesting methods here. I think IA3 is an overlooked method. It was introduced in TFU paper, and its idea was to just add some scalar weights to the model. So what you're adding here is you're going inside the multi-head attention, and after you computed your keys, queries, and values, you just multiply them by a trainable vector. Just like not even dot product, just parameter per parameter multiply. So like head-and-mark product or like element-wise product. And then you go inside the block of fully connected network, and you do the same with the hidden state. So you have this IA3 scaling inside the hidden state of the fully connected network. And this shows, again, incredible performance. And we'll talk more about this. But what I want to show you here is how diverse these methods really are. It is not just adapters or just LORA. We see a lot of interesting ideas if we start looking into these methods. Next big category is selective methods. And one of the first one here was not even BitFit. You can think of selective parameter efficient fine-tuning in the context of just fine-tuning the last layer. It was super popular in computer vision. It was relatively popular in the era of BERT. Like, let's just fine-tune the last layer. In a way, that's a selective parameter efficient fine-tuning. You're not tuning the whole network. And BitFit suggested that, okay, let's actually just fine-tune the biases of the network. And it showed pretty good performance in the original paper. Unfortunately, it doesn't seem to scale well to large networks. But amazing thing is the pseudocode actually works. So the rest of the pseudocode you kind of need to modify to make it work. But BitFit is literally just one line of code. You define your parameters that you train as like if it has bias in the name, at least in PyTorch, this is how it works. And it can give you like performance comparable to full fine-tuning at smaller models. Freeze and reconfigure is another like overlooked method. It tries to be kind of like selective, but not per parameter selective or per block selective. Instead, it selects the rows of your matrices that you want to update, or actually columns, not the rows. The idea is you use some measure. Maybe you use information measure, maybe you use gradient measure, but like you need to select some of the columns that seems to be more important for your task. You can just use like magnitude selection. Now, after you selected them, you split all of your linear layers into two matrices, a frozen matrix and a trainable matrix. And then you only train a trainable matrix, like some of these green columns. After training, you can reconfigure it back, so you have no inference overhead. And again, it works pretty well at smaller models and have not been evaluated at larger models. And the final big like area of parameter fine-tuning is reparametrization-based methods. Reparametrization-based methods probably were introduced like by LORA, and their idea was you kind of don't need to have as many parameters as like adapters say. You can say, I'm going to update a lot of parameters, but do this in a parameter efficient way. For example, what LORA does, it says, we want to update matrix W that's potentially pretty big, like let's say 1,000 by 1,000. But we really expect that we don't need to modify our network a lot in terms of the rank of the change. So what we do is we decompose our update into two matrices, WA and WB. And WA is something like 1,000 by 5, and WB is like 5 by 1,000. So when multiplied, they give you 1,000 by 1,000 matrix, and you can update your weights. But they are way more parameter efficient. Like if this is what you have, is like 1,000 times 5, like 5,000. You have just 10,000 parameters instead of 1,000 by 1,000 parameters. And LORA is super easy to implement, so like implement like a number of times. And there's like this little mistake I always do with the scale, but you also need to scale it. Actually, I think I still have a mistake on the slide. You need to scale it here when you do h plus equal x, not here. And it works really well. I think it's really started gaining popularity with the release of Stable Diffusion. And Stable Diffusion is like relatively large. It's like about 1 billion parameters total. So people were inserting these LORA layers if you want to modify how Stable Diffusion like models particular styles or something like this. And now there are many implementations that you can just use. And LORA is like super popular. Like everybody who is like at least into a bit of parameter efficient fine-tuning knows about LORA. But there are many like extensions and modifications. For example, KronA suggested that we're gonna generate this W matrix, not using matrix product, but using Kronecker product. And if you don't know what Kronecker product is, it's also sometimes called tensor product. This is how it works. You have a matrix A and a matrix B, and you make a new matrix where you say, take the whole B matrix and multiply it by A11, and it's going to be this block, and then A12, A1n, and so on. And your final matrix is like hugely inflated. It's going to be like basically like A, if A has the size of like m times n, and B has size m times n, it's going to be m squared times n squared. So that's pretty impressive in terms of like how much it inflates the dimensionality, or another way of saying this, how much it saves you parameters. So you can update this many parameters by having just this many parameters. And this is like a rough implementation of KronA. You do, again, regular linear, and then you compute this kind of like residual, in a way, connection that is x times the matrix that is made of Kronecker product of WA and WB. And you can do this efficiently without computing the whole matrix WA times WB with this code. So KronA is more memory efficient than LORA and gives you pretty much the same performance. And then there is the whole realm of hybrid approaches. People connect together adapters and prompts. For example, MEM adapters explored different methods. I think they explored adapters, they explored soft prompts, they explored BitFit and something else, and experimented a bit. And what they said is, let's do two things. First, instead of inserting adapter right here, like after, like right after adapter or like right after multi-head attention, let's insert it in parallel. And the second thing they noticed is, if you add just a bit of parameters to the soft prompt, it can really improve your performance. So we're like, okay, let's just mix and match these two approaches. BitFit didn't work for them, unfortunately, but these two made really good performance. And it's pretty easy to implement if you know how to implement soft prompts or adapters. Next thing is compactor. Compactor combines the idea of reparametrization and the idea of adapters. So it reparameterizes the parameters of the adapters into like less parameters. And it's like, I think maybe like one of the most complicated methods, but you can still fit it into like 6 lines of code. So the idea is you use compactor as your adapter. And here you do like LPHM of X, which is essentially just a linear layer. And what you do here in LPHM forward, you first compute your matrix B, which is kind of this matrix that you're going to use for your weights. This is just like a dot product. And then you do a Kronecker product between a matrix A and a matrix B. So you have 3 trainable matrices for every linear layer. You have matrix A, matrix B sub D, and B sub U. This is super parameter efficient. Like, it is much more parameter efficient than adapters, or I think even LORA. And then you just compute this, and in a way, this is a linear layer, but with certain restrictions on what operations it can perform. But our neural networks are so flexible that even by modifying them a bit, you can get really, really good performance. And like, as far as this method, it just takes all of the methods and does a big hyperparameter search of like, what is the optimal way to combine them? So they combined adapters, prefix tuning, BitFit, and LORA. And they say that, okay, let's split your network into 4 groups. The first group is going to be like relatively small. The middle groups are going to be relatively large. And the final group is going to be, again, pretty small. And for the first group, apply adapters and LORA. For the second group, adapters and prefix tuning. For the third group, adapters, prefix tuning, and BitFit. And for the fourth group, prefix tuning, BitFit, and LORA. And at 0.1% additional parameters, they got like some, not huge, but consistent improvement over like any other combinations of these methods. So if you go into our paper, this is the huge table you'll find where we try to categorize all of these methods. And we also try to say, okay, does this method save you storage? So like, if you train a network with this, do you need to store a lot of updated parameters? And here, most of the methods do this. Then we ask, does this specific method actually improve your memory? So some of the parameter efficient methods actually do not improve your memory usage. For example, BIF pruning, what it does, it trains your network as usual, but in parallel, it also trains a special mask. So that after training, you can say, I only need to update 1.0% of my network, and I know which ones that I learned a special mask for them. And after this training, you can only store these like 1% of your parameters. But during training, you need to like learn all of them, which is kind of problematic, and it is parameter efficient in terms of the storage, but it is not parameter efficient in terms of the memory. Also, some of the methods, they actually allow you not to backpropagate to your original network, or like save on backpropagation sometime, which just increases training speed. There are a few of these methods. I think next time I should probably cover one of them during the presentation. But there are some trade-offs here. So if you go into inference overhead, some of these methods don't have any inference overhead because you can integrate your parameters, your update into your network and get more or less the same network. While in case of adapters, you need to compute this extra fully connected network. It's not big, but it's still there. So for all of these methods that don't backpropagate into the network, they train something else. So you're cheaper at training, but you're a bit more expensive at inference. So I kind of started talking about this, that parameter efficient fine-tuning methods are kind of hard to compare. There is a number of parameters that everybody reports, but honestly, there are 3 numbers that all can mean like the size of the update. First is the number of trainable parameters. Second is the number of change parameters. And third is kind of this rank of the total update of your network. And trainable parameters are usually correlated with the amount of memory that you're going to use. And I feel right now, this is what's mostly important. The number of change parameters talks about the storage constraints. So if you have like some crazy multitask setup where you have hundreds of tasks, or that you need to run on a phone, you're kind of worried about the storage and maybe not so much about memory. And then the rank of the delta is, I would say, mostly theoretical, but some of the methods here are like intrinsic SAID. They update the whole network, but they do this in a way that is constrained just in terms of the algebra of it. specifically in the rank. And most of the existing papers do not distinguish between these. So if you take a look into the paper, you'll need to really carefully read it. For example, I thought that diff pruning is actually an efficient method during training, but turns out it's not. And we try to highlight the cases where the number of trainable parameters is different from the number of changed parameters. So we have these in bold. You see diff pruning. Here you need to train 200 parameters compared to full fine-tuning, but you only like update half of them, like 0.5% of your parameters. And then there are like a few more changes here. And another thing that we really try to summarize and highlight was this method evaluated at large scale, because we're not interested fine-tuning like less than 1 billion parameter models with PEFT methods. Like 1 billion parameter models is not a lot. You can easily fine-tune this like on a 3090. But if you have something like 10 billion or something more than 20 billion, you're really, really worried about this. And you want not just to save memory, you kind of want to know that you can achieve similar performance to full fine-tuning, or like just best possible performance, like by updating this many parameters. And methods like adapters, BitFit, prompt tuning, prefix tuning, and LORA were evaluated at even like 100 billion scale, but many of them weren't. And for the BitFit, for example, we found that, like as a community, we found that for like 10 billion parameter networks and for like more than 20 billion parameter networks, BitFit doesn't work well. So some of these methods can really change if you apply them to different networks. So again, what matters in PEFT? Number of parameters that we probably train, the training efficiency, because again, it depends on how expensive your method is. For example, KronA, which uses Reconfigure product, is more cheap than I think. Yeah, I think KronA is cheaper than Compactor, even though they both use Reconfigure products. But in Compactor, you cannot use this hack of combining the updates of the parameters with like multiplying your vector times your Reconfigure product without actually computing Reconfigure product. Probably this is confusing, but main point is implementation matters, and some of the parameter efficient fine-tuning methods can be efficient at training or inference time in terms of the compute, and some could be less efficient. And this does not necessarily correlate to the number of parameters. And the final one is inference efficiency. If now we are deploying these like huge language models to the world, we kind of want them to be as cheap as possible to deploy. So you don't want to have adapters. Probably you don't want to have adapters in your large language model because they give you this overhead. LoRa doesn't give you the overhead, and this is one of the reasons why this method is so popular. And final is accuracy. Do we get good performance out of the network in the end? Some of the parameters, some of the PEFT methods give you really good performance. Some give you slightly worse performance, and we reviewed all of them in the paper, but it's really hard to compare them because you have this x-axis of how many parameters you really update. You have this another x-axis, which is like how expensive training is. You have another axis of how quick the inference is. And only after setting all of these kind of to the same setup, you compute your accuracy, and you need to compare different models with different trade-offs. So this is really one of the big issues we saw in all of these papers. There is a big lack of standard benchmarks, because we need to standardize not just the data sets, we need to standardize the models that we are fine-tuning. So like a specific model, for example, like T5XL, and like, let's see if your method works specifically with T5XL, because we want to compare in the same setup. We need good metrics. We need good metrics to control memory usage, because again, trainable parameters, so like some number of parameters, does not necessarily correlate with the memory. You need to explicitly measure the memory. And you can have different restrictions here. For example, like you cannot have more than 40 gigs of RAM. Like if your method, like at least for a second, goes out of 40 gigs of RAM, this is not going to work for our GPUs. So really it would be great to have some standard benchmark that just gives you a specific instance on like AWS or Google Cloud and says, this is your GPU, you have this much compute time. Now just go your method and try to get the best possible performance on this model on this data set. So taking a small step back and talking about model size. A pretty interesting thing is larger models require fewer parameters to be updated during fine-tuning. This is a bit counterintuitive because it is not just in the percentage. Actually, the number could be smaller in absolute numbers. If you go into the prefix tuning paper, I think, they evaluated the method on multiple T5 sizes or just language model sizes. And what they found was that to get the same performance as full network, you need to update, let's say, 10,000 parameters for like 100 million size model. But for like 10 billion size model, you also need to update 10,000 parameters. And like, it's actually possible if you go beyond 10 billion, this number becomes even smaller. So you cannot just compare percentages if you have different size models, and you need to evaluate your method at different sizes that like people actually care about. So I think fixing some of these problems is definitely a future direction for our community, but also just to motivate more, okay, which directions can we go? What are interesting new methods that we can find is probably more hyperparameter robust methods or just the studies of how to tune hyperparameters. There is a very big difference between regular fine-tuning and parameter efficient fine-tuning. If you remember your deep learning classes, your learning rate really strongly depends on the number of trainable parameters in your network. And if you train 1 billion parameters, you have to have a like higher learning rate, like lower learning rate than if you train just like a few thousand of parameters. And I have not yet seen good studies on like how we need to change our hyperparameters when we do like LORA, when we do adapters. Then I think a good direction would be looking into more methods like KronA products. Like, can we make even more efficient reparametrizations? Reparametrizations that give you more flexible update of your network, like higher rank of the modification for a lower parameter count. And another thing is you go through these papers and you think some of them really like tune this specific part of the network. But also we know that networks really differ in terms of what layers produce what features. We saw a lot of model analysis papers, and they say that, for example, like BERT really has like super abstract features in like the second to last layer and like layer before that, but it has like really low abstraction, like localized features in the first layers. And also like the very last layer is also kind of localized because BERT needs to kind of like decode your hidden states back into the meaning of the words because it needs to predict these words. So I think we have a lot of interesting information model analysis literature that can inspire future PEFT methods. And the final thought that I had like writing this paper was there's a field of edge machine learning, and edge machine learning, like they have a lot of issues. They never have enough memory. They never have enough storage. They never have like enough electricity. And we are kind of in the same place right now. Like our whole field is bounded by the memory. When you train huge models, you even care about how much electricity they cause because it's different amount of carbon dioxide that you throw into the world and can be insignificant. And if you deploy things, you are worried about storage. So really, I think getting into edge machine learning field, getting into their papers, which are quite different from the papers that we usually read, can really inspire more methods, and like collaboration in this field could be really, really fruitful. So now we discussed many methods. How do you actually use them? There are 3 pretty good libraries. There's Adapter Transformer, so like Adapter Hub, which doesn't just have adapters, it has a lot of other methods, LORA, like MAM and other methods. There's Hugging Face PEFT, a new library that came out like about a month or two ago. And there they try to support as many Hugging Face models and as many PEFT methods as possible. And there is also Open Delta, which is a library from one of the papers. I took a look at it. It looked pretty good, and it had a bit more implementations of methods than I think PEFT at the time. So definitely worth checking out. And now kind of what we're trying to do, there's like a small collaboration that starts now, and we're thinking of, let's try to implement a lot of PEFT methods in super minimalistic fashion just for one architecture. So it's not too big of a work. We chose LLaMA because LLaMA is pretty cool. Maybe we're gonna change this to something more open because LLaMA checkpoints are kind of tricky to get. We try to implement just as many methods as possible, so we have the standard benchmark. So everybody is welcome to contribute. I didn't have a lot of time in the last week or two to do this because of the NeurIPS deadline, but we're definitely going to continue work after NeurIPS. So thank you all for listening. If you're interested in the paper, check it out. Also, if you like this way of reading the paper of like having a pseudocode and having a one-sentence idea, this is exactly what we have in the paper. So you go to the method, we're going to bold this one-sentence idea that describes the method. And for most of the methods, we also have a pseudocode so you can understand it easily. So you don't have to like really read whole 15 pages. You can just skim through it and get more like 90% of what you can get from the paper just from the skimming. So I think I have like one more like extra slide if we had the time. And I think we still have like a few minutes. This paper, Intrinsic Dimensionality, explains the effectiveness of language model fine-tuning. Is often overlooked, but it has really cool like theoretical / empirical results on how the models are affected by the pre-training and how they're affected by the fine-tuning. And one of their results was the longer you pre-train, the less you need to update your network to a certain task in terms of the rank of the change. So really worth checking it out. Their method, like Intrinsic said, is not practical, but their findings are pretty amazing. So now, any questions that we all left?
Thanks, Vlad. This was very cool, very encyclopedic. We do have some chat questions, so I'm going to read them chronologically. So the first one was from Oleg. He is asking, referring back to your previous answer, can any of these methods they'll be used or be a foundation for distillation approaches, basically meaning having limited computational power or something, but the necessity to distill the huge models knowledge into something small and compact? I hope.
Okay, this is a interesting question. I didn't think about this. I should note this. I think there could be some relations and there could be some ideas in between these two fields. Nothing obvious comes to mind, but because like parameter efficient fine-tuning kind of assumes that you have a well pre-trained network that you need to just adapt a bit. Like right now I'm working on something that sees like, can we really do this during pre-training stage? Can we make pre-training cheaper using these methods? And the answer is complicated. But in terms of the distillation, it would be interesting to take a look. I don't have any obvious ideas in mind, but thanks for highlighting this.
Next question comes from Arena. But the differently sized models have different starting points for fine-tuning. Shouldn't we compare the number of parameters to get the same gain in performance then, is the question.
Okay, differently sized models have different starting points. So I think my point was that you need to compare this number of parameters and the models. Like there are many things that you need to align to really have a correct comparison between methods. So like definitely, yes, we need to compare the number of parameters. but we also need to compare like what exact checkpoint you're fine-tuning from.
Thank you. Next question, before we also get some live questions, is what about PEFT method on decoder-like models? How does it work on classification, task, or named entity recognition?
Okay. I think like all of these methods, they're not specific to like specific architecture, and like decoder like models are just transformers with causal masking. So plus yeah, okay, like I guess the original like adapters were evaluated on BERT, but for example, prefix tuning was mostly evaluated on generative models. So it is like the results are closer in terms of the domain, but I wouldn't expect to see a lot of difference between like encoder only, decoder only, sequence to sequence models here.
I see. Oleg also is asking, can you please maybe give some practical insights, if any, from your research on choosing the right or state-of-the-art method for practical tasks currently?
So as of now, like LORA is a really nice and simple method that consistently gives you good performance. There are some tasks, if you go into the literature, where LORA underperforms some methods. So like it doesn't always give you the same performance as full fine-tuning. So if you want to really go deeper, the LORA is a great baseline choice. I'm really interested in testing IA3 more. And I'm really interested in looking more into KronA-based reparametrizations like KronA or like Compactor. And I see a question about GitHub link from the last slides. I can share it in chat, I guess, but I also will share a link to this presentation so everybody can access this after. So the GitHub is here. There you go.
So we're going to share them also in the YouTube description when we post it on YouTube. So Alexander's question was answered. So do you feel like we have, this is very relevant to the whole subject that you talked about, but do you feel like we have finally entered the era of not necessarily scaling up to infinity? And I mean, even until last year, it was kind of a race, and now it feels like so many models with a tenth of some state-of-the-art models achieve the same, if not better performance. So do you feel like we have finally entered the era of efficiency and not necessarily scaling up to infinity, or do you think we have a little bit more work to do?
Yeah, that's a great question. Like, I think the answer is pretty complicated. So like scaling laws are still there. Scaling laws, they're kind of like Newton laws, and you cannot really avoid them. At least we haven't found the way to avoid them yet. So what happened recently is that people were saying that really compute efficiency in terms of chinchilla efficiency is not important. You can train models and they're going to train on more tokens than we need them to train on in terms of compute efficiency. If you're worried about something that is not just benchmarks, if you're worried about benchmarks and you want to pre-train the best network possible, then yes. But if you're worried about real applications and real deployment, you want the models to be smaller, and turns out you can train relatively small models like 1 billion or 10 billion parameters. And if you train them on 1 trillion tokens instead of compute optimal 2 billion, I think like for 1 billion, compute optimal is about 2 billion tokens, or 20, I think 20 billion tokens. Yeah. So if instead of 20 billion tokens, you train on 1 trillion, this 1 billion parameter model, it doesn't go like exactly like 175 billion compute optimal model, but it gets relatively close. There is a limit to this. So we definitely want to scale up when we can in terms of inference time, and we are going to continue scaling in terms of the data amounts. My guess is next questions in the industry are going to be, where do you get high quality data? If you listened to Lex Fridman podcast with Sam Altman, which was pretty amazing, I really recommend listening to it. Sam Altman did mention that they feel at some point they're just gonna not have enough data to like train the next generation of the model. Like at some point you trained on like most of the internet, and where do you go next? Or like at some point you trained on all of the publicly available data, but can you maybe like get some data that's not publicly available, like buy data? For example, for DALL-E, if I remember correctly, DALL-E 2 was trained not on publicly available data, but on data that OpenAI bought from Shutterstock. It also like simplifies some of the legal issues of this, but my main point is we're going to continue scaling over the data. We're probably going to continue scaling over the model size, but slower, because like our GPUs become better. Like you can now inference 1 billion or parameter model like pretty easily on your MacBook or your iPhone. So as hardware improves, our model sizes will continue to improve and increase. Maybe, hopefully, model size is not going to grow faster than our computational resources for the inference. But in terms of pre-training and in terms of the number of data we use for it, it's only going to go up from this.
It almost feels like after all of the proprietary models were making incredible advances, and then the open source community fired back, and now it's kind of getting evened out. And at some point, maybe if we run out of data and there is no more data to train on, then money is going to come into the game again, and the rich corporations are going to be able to buy data because there will be no more data. I mean, it's hypothetical, but yeah.
Yeah, like large corporations are also more restricted in what exact data they can use. Like some people speculate that LLaMA has this non-commercial license, not just because Facebook doesn't want you to use LLaMA commercially, but also because Facebook is worried that some of the data that they use for pre-training might not allow commercial use.
Just one last question. I think I saw this as a discussion in Twitter today. It was kind of interesting about how much is being talked about open source these days, but so many things are not really open source. I mean, sometimes they're just open core or something like this, but they're advertised as open source. And it was kind of an interesting discussion how so many things are advertised as open source, but they are for sure legally in the legal definition of open source, they are not open source. So I was just interesting to think what you think about it.
Yeah, I think I saw something like this like a few times too. I believe like some of the issues that I saw people were raising, for example, the new licenses by Big Science, like the Bloom license, does not allow you to like it says like you need to use our models for good, you cannot use our models for harm. And in a way, this contradicts open source licenses, I think. But my thought is this is not the seminal question, at least for now. And what's more interested in legal space is like there are a couple of lawsuits that's going on right now. There is a lawsuit on GitHub Copilot. There is a lawsuit on LLaMA. They're like, I mean, on like leaking the weights. I really don't like the word leak because like weights were released for researchers. But the word leaked sounds like somebody stole it from Facebook. So yeah, I think we're gonna see a lot of really interesting and worrying things in the legal space. Hopefully it's gonna be for the best in the end. But yeah, the field now is very different than it was like before ChatGPT. Everybody is looking into AI, and I kind of would like our field to be a bit less popular nowadays.
Good point. at the end, we usually ask people about a paper that they have recently read and enjoyed. It can be a large language model or NLP paper, or it could be computer vision or something that you found interesting. Just
I need to think about this. Like the last few weeks, I've been working, trying to get to meet Europe's deadline. There definitely was something. Let me take a quick look. So maybe, yeah, like quick announcements. I made like a new Telegram channel just for links, without any comments on them. I will post in my Lialin NLP channel about this. I'm taking a look at it right now, and I really wanted to read Author. It is a multimodal model with in-context instruction tuning. So it's kind of like Flamingo of the last year, but Otter was much cheaper to train. So I will share a link to it. I haven't yet read it, but it is definitely at the top of my list. And another one that I think is pretty interesting. Language models can explain neurons in language models by OpenAI. So OpenAI continues to publish research, which is pretty good, though less than we saw before. But this is a pretty incredible team, and even though they're not as open as we would like, they do share some interesting research.
thank you. We are going to put all of them in the YouTube description as well. So yes, there's still quite a lot of people in the meeting. If anyone has any more questions, you can just unmute yourself, or if you don't want to speak, you can put it in chat. And yeah, this was very interesting, very informative. The paper, if anyone has not read the paper, I highly recommend it. It's very nicely written, and yeah, so thank you everybody for coming. Thank you, Vlad, for participating and honoring the 1 year anniversary as first and now most recent speaker. And
maybe make the tradition.
yeah, so
we will have the cake at New Rips hopefully together.
yeah, and next year, 2024, when we're probably gonna have, I don't know, GPT-6 with 100 trillion parameters, maybe we can meet again at on 11th of May, and you can speak about it or something.
It would be great. Thanks for having me. It was great to present here.
Absolute honor to have you. Thank you very much. And for those who don't know, he has also a Telegram channel in Russian language. We'll also link in the description. Check out. He has some pretty decent insights and gems about NLP. Thank you once again, Vlad, and wish you all the best in your research.
Thank you. Thank you.
Thank you.
Everybody have a good one, and bye.
Thank you. Bye.
Thank you. Bye, and see you soon.
See you soon.